In section 3, we are going to talk about discrete and continuous random variables. We are going to focus mainly on discrete random variables, as in chapters 5, 6, and 7, we're going to focus on continuous random variables. So go ahead and talk about what a discrete random variable is. We're going to take a look at an example. So let's go back to the example where we toss a coin 3 times. So we already know that we have 8 outcomes for the sample space. We can get heads 3 times, tails 3 times, and then we have our combination of getting 2 heads and then 1 heads. So that gives our total of our 8 outcomes. So the probability of any one outcome, so whether that's heads or tails, is going to be 1/8. So when we look at it, so if we let x, our variable, be the number of heads out of 3 coin tosses, we can have x equals 0, which means you have no heads in 3 tosses, which that only happens 1 time, so 1/8. You can have x equals 1, which means you get 1 head in 3 tosses, which we've discussed. There are 3 different ways to do that. You can get x equals 2, which is 2 heads in 3 tosses, which is also 3/8. Or you can have x equals 3, which is 3 heads in 3 tosses, which is 1/8. So if we create a probability distribution out of this, we create a table where x is our number of outcomes, which in this case is 0, 1, 2, or 3, and then p of x is our probability. So we write it as 1/8, 3/8, 3/8, and 1/8. Which we can then use to find probabilities from this table. So just like a regular probability distribution, all of my probabilities have to add to 1, and 1 plus 3 plus 3 plus 1 is 8, so I get 8 out of 8, which is 1. So I can find the probability that x is exactly 2, which we know is 3 out of 8. You can also do inequalities. So the probability that x is greater than or equal to 2 is the probability that x is 2 or x is 3. So I have to add the probability that x is 2 plus the probability that x is 3. So that's 3/8 plus 1/8, which is 4/8, which is the same thing as 1/2. We can also do an inequality like less than. So the probability that x is less than 2. Now the strictly less than here does matter. So all of the ones less than 2 are x equals 0 and x equals 1. So I do the probability that x equals 0 plus the probability that x equals 1. So that's 1/8 plus 3/8, which is 4/8, which is 1/2 as well. Now, if it had said less than or equal to 2, then I would have also added the probability that x is 2, which has changed my probability. So having that equal to does matter. So a random variable, just kind of review from when we're talking about probability, takes a numerical value that describes the outcomes of some chance process. So we usually use a capital letter to denote that random variable. Usually it's x, it does not have to be. Random variables can be discrete or continuous, but they have to be numeric in value. So the first type we're going to talk about is a discrete random variable. So that's when x takes on a fixed set of possible outcomes and has distinct values. So that usually means no decimals and sometimes not every number. Probability distribution of a discrete random variable x lists the values x and their probabilities. And we do this most commonly with a table. You could actually do a histogram as well, but we're going to focus with a table. So very similar to a regular probability distribution is that every probability is between 0 and 1, and the sum of the probabilities is 1. So let's take a look at an example. So you put all the letters of the alphabet in a hat, so A through Z. If you choose a consonant, I pay you $1, and if you choose a vowel, I pay you $5. X is a random variable representing the outcome of the experiment, so we want to create a distribution for X. So when I create my table, I'm going to have X and probability of X. So my outcomes here, so what does X mean? X is the amount I pay you. So I can either pay you $1 or I can pay you $5. Those are my two outcomes. Now I need to do my probability. So I pay you $1 if you choose a consonant. So if you're thinking consonants, that's A, B, C, D, F, so everything but the vowels, which there are 21 consonants, so 21 out of 26. $5, you get $5 if you get a vowel, which is A, E, I, O, and U, not Y, just A, E, I, O, and U, which there are 5 of, so 5 out of 26. And that's my probability distribution, just those two. With a continuous random variable, it takes on all possible values in an interval of numbers. So it's usually described by a density curve. So think back to chapter 1.4 when we're talking about the normal distribution. We talked about density curves. Continuous random variables are described by a density curve, which is why we're going to focus mainly on it in chapters 5, 6, and 7, and not so much in chapter 4. So for continuous random variables, the probability of any event is the area under the density curve and above the values of X that make up that area. And just kind of refresh, the area under that density curve is 1. So we're talking about discrete versus continuous random variables. Couple things to know. An equal to inequality does not matter for a continuous random variable, and we'll talk about that more in chapter 5. Equal to inequalities do matter for discrete random variables, however. Discrete random variables are often described with a table or histogram. Again, we're going to focus on a table. And continuous random variables can only be described with a density curve. So with discrete random variables, we can actually calculate its mean or its expected value. So X is whatever our numerical outcome is of our random event. And instead of using our symbol for mean, mu, we use E of X, and it stands for expected value of X when many trials are run. So expected value is the same thing as mean. However, we don't calculate it the same way we would a traditional mean, which is why we kind of use expected value, because there's a different way to calculate it. So what you do is you multiply each possible value by its probability and then add all of those products together. So if I have my outcomes x1, x2, all the way up to x sub n, and I have my probabilities, so probability 1, probability 2, all the way up to whatever my nth probability is. The formula, if you write it out, is E of X equals x1 p1 plus x2 p2 all the way up to whatever your nth value and probability is. So however many values are in your table. The compact formula, using like summation notation, expected value of X is the summation starting from your first term to your nth term of X sub I, P sub I. And we're going to do an example of this so you can see it's actually a fairly easy formula to use. So in our example, we have that Northwestern University posts the grade distributions for its courses online. Students in Statistics 101 in a recent semester received 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. You choose the Statistics 101 student at random. The student's grade on a 4-point scale with A equaling 4 is the discrete random variable X with this probability distribution. So we're going to go ahead and create our probability distribution. So X and P of X. So we have A, B, C, D, and F, which is on a 4-point scale. So an A corresponds to a 4, a B a 3, a C a 2, a D a 1, and an F would be a 0. So the percent of A's, my probability is going to be 0.26, a B is 0.42, a 2 is 0.20, a 1 is 0.10, and a 0 is 0.02. All right, so we want to say in words what the meaning of probability X greater than 3 is, and what is that probability. So a probability of X being greater than or equal to 3 is you earn a B or higher. So the way I find that probability is I do 0.26 plus 0.42, which is 0.68. Next, we're going to write the event that a student got a grade worse than C in terms of our values, and then find that probability. So C corresponds to a 2. Anything less than 2 is going to be X less than 2. Now, it does not say that a student got a C or worse. It says that a student got a grade worse than C. So that is strictly less than. So there's no equal to, which means everything less than 2 is my 0 and my 1. So I do 0.10 plus 0.02, which is 0.12. So now let's go ahead and calculate our mean, and then we're going to interpret it in the context of our situation. So my expected value is 4 times 0.26, because that's its probability, plus 3 times 0.42, plus 2 times 0.20, plus 1 times 0.10, plus 0 times 0.02. So every outcome X multiplied by its specific probability added together, which is going to equal 2.8. So my expected outcome is a 2.8. So what that tells me is that in the long run, because all of our probabilities are in the long run, we expect a random student to get between A, B, and C in the course. So 2.8 is somewhere between a B and a C. It's slightly above a C, but slightly below a B. So it's somewhere in that range. And that's our expected value. The last thing we're going to talk about is variance and standard deviation. So just like when we were doing this before, we can do it as well with a discrete random variable. And the formula is not the same as it is for just a regular standard deviation. So it does still measure how much the values of the variable typically vary from the expected value. So the definition hasn't changed. It's just how we calculate it. So it starts off the same way. So you have your table of values, x1, x2, all the way up to x sub n, with their corresponding probabilities. But the way we calculate our variance is we are going to subtract from each value our mean and square it, then multiply it by its probability. So whatever x1 is minus whatever your expected value is squared, times its corresponding probability. And then we keep adding for every value in the distribution up until you reach your last value. So if you think in terms of condensed formula, so that's the sum starting from your first term to your last term of x sub I minus your mean squared times p sub I. So that's the variance, and similar to when we calculated standard deviation, we just took the square root of the variance, we did the same thing here. My standard deviation is just the square root of that sum. So let's do an example where we find our expected value and our standard deviation. So the daily lottery costs $1 to play. You pick a 3-digit number. If you win $500. So we want to find the expected value of the lottery and the standard deviation. So in this case, there are two outcomes. There's either you win or you lose. So X is your expected winnings. So X equals your winnings. So in this case, you could win nothing. You could lose, in which case you are out $1, which means you're actually at -1. You're not at 0 because it cost you something to play. So if it costs you something, you have to take that out of your potential winnings. And if you win, instead of winning $500, you actually win $499 because, again, it cost you $1 to play. If we're dealing with a 3-digit number, we're dealing between any number between 1 and 999, of which there are 1,000 numbers. So the probability you lose, since there's only one winning ticket, is 999 out of 1,000. And the probability you win is 1 out of 1,000. Those are your only two probabilities. So for my expected value, you have to do -1 times 999 over 1,000 plus 499 times 1 over 1,000. So that gives you an expected value of -0.5, which means you're expected to lose 50 cents every time you play this game. So first we're going to calculate for the next thing our variance. So my variance is take my outcome x, -1, subtract your mean, which in this case is negative, so I have to do -1 minus -0.5 squared, times the probability, 999 over 1,000, and then plus my second outcome, 499 minus -0.5 squared times its probability, one over 1,000. So what you can do is you can type that exactly as it appears in your calculator. And it's going to give you a variance of 249.75. Remember, that's my variance. My standard deviation is then the square root of that number. So my variance in this case is 15.8. So even though I'm expected to lose 50 cents when I play the game, my variance is 15.8, which means my typical winnings vary by $15.80 every time I play the game, which means I could be above that or I could be below that. So I could actually come out positive, I could win, or I could lose even more money based on that. Okay. Last example, we have that a pair of dice is rolled. Depending on the sum of the dots on both dice, Cole can win or lose money as shown in the following chart. Should Cole play the game? Explain your answer. So we want to know, if we're trying to determine should Cole play the game, we want to know, will he win? What is his expected value when he plays the game? So we're going to find our mean. So the first thing we want to do is convert that table to a probability distribution. So my x and my probability of x. So if I trying to convert this to a table, I'm just going to go straight as it appears. I don't have to put it in any specific order. So my first outcome is that he could win $6, so that's a positive 6. He could lose 4, which is negative 4. He could win 7, so positive 7. He could win 5, so positive 5. And then lastly, he could lose $1, negative 1. So those are my outcomes. Next, I want to convert my outcomes to probability. So this has to deal with rolling a pair of dice. So if you remember, there are 36 outcomes when you roll a pair of dice. So the first one, winning $6, comes from getting a sum of a 6 or 8 or 9. So if you're thinking about how many outcomes that is, so to get a 6, there are 5 outcomes. To get an 8, there are also 5 outcomes. And to get to 9, there are 4 outcomes. So that gives me a probability of 14 out of 36. To lose $4, you have to get a 2, a 4, or a 5. So there's one way to get a 2. There's 3 ways to get a 4. And there are 4 ways to get a 5. So that gives you 8 out of 36. To win $7, you have to get a 10, of which there are 3 ways to get a 10. So that's 3 out of 36. To win $5, you have to get a 3 or a 12. There's 2 ways to roll a 3, 1 way to get a 12. So that's also 3 out of 36. And you lose $1 if you get a 7 or 11. And there's 6 ways to get a 7. And there are 2 ways to get 11. So that is 8 out of 36. And if we check, we add 14 plus 8 plus 3 plus 3 plus 8. That is all of the potential outcomes when rolling 2 dice. So we do have a probability distribution. So when it comes to calculating my expected value, I'm going to do 6 times 14 out of 36 plus negative 4 times 8 out of 36 plus 7 times 3 out of 36 plus 5 times 3 out of 36 plus negative 1 times 8 out of 36. So when I plug that into a calculator, I'm going to get an expected value of 2.22. So that tells me my expected outcome, my expected winnings in this case, are $2.22 when I play this game in the long run. So if it comes back, should Cole play the game? Yes, Cole should play the game. Because he is expected to win $2.22. If my outcome had been smaller, like 0.02, I don't know that I'd necessarily, even though you're winning, it's not a lot of money that you're winning in the grand scheme of things, considering you can only win up to $7, 0.02, not very high. Obviously, if you get a negative value, you should never play because you're going to lose. But just because you get a positive value doesn't necessarily mean you should always be like, yay, I'm going to win. Take it in context of what the most you can win is. So $2.22 when you can win up to 7, that's a pretty large value in the grand scheme of things. If I could win up to $700 and my expected winnings were $2.22, I don't know that I'd necessarily play because I'm not expected to win that much. It also depends on if it costs you something to play the game as well. So let me know if you have any questions about discrete or continuous random variables, and then finding mean or standard deviation with a discrete random variable.